And now I have another example that is useful for us to spend some time on. This is another table out of the American Journal of Public Health. It looks at socio-demographic attributes, health status, and use of health services for some different major ethnic groups. And this relates to children. Now, I've highlighted here, or circled, or boxed, better to say, the issue that I would like to examine is bed days for illness in the past year, mean plus or minus SE. And that means standard error, we presume. And you see we have a mean of 3.3 for the mainland Puerto Ricans on the sample of 1,383. We have a mean for Cuban Americans, a sample of size 357 of 2.4. The standard error for the mainland Puerto Rican sample is 0.2, and the standard error for the Cuban American sample is 0.7. So that's the information that we have from this experiment. We have fairly sizable samples. The hypothesis that I would like to test is whether or not the mean bed days for illness in the past year is different for mainland Puerto Ricans and Cuban Americans. So, and this slide shows you the reference information. We have the sample sizes listed, the means, and the standard errors. And remember that the standard error is S divided by the square root of n. So to use the formula that we've been working with, we need to get back to S and S squared. So if the standard error is equal to S over the square root of n, then a simple algebraic manipulation says that S is equal to the standard error times the square root of n. So if the standard error is 0.2 for the mainland Puerto Ricans, then this S is 0.2 times the square root of n, which is the square root of 1,383. Do that calculation, you get 7.44. You square that and you get the sample variance, which is 55.35. If you do a similar thing for the Cuban Americans, you get a sample standard variance of 175.03. Now these two sample variances are quite far apart, and in fact they may well be sufficiently far apart for us to reject the null hypothesis that they came from populations having the two variances, but the same variance. But I won't deal with that issue now. I want to use this as an example for the regular test. But again, I'll show you how to deal with that later. All right. We have our 7 steps to go through. Mu1, the first one is the null hypothesis. For the hypotheses, H sub naught is equal to mu1 minus mu2 versus mu1 versus H sub 1, I should say, mu1 not equal to mu2. We're assuming we have independent random samples from normal distributions, and that these two populations have the same variance, and we'll call that common variance sigma squared. We're going to use alpha equal to 0.05. And we're going to use the test statistic that we've been using in this module, namely that t is equal to x1 bar minus x2 bar over the standard error of that difference. And that standard error is s sub p times the square root of 1 over n1 plus 1 over n2. If you do that calculation, you'll start that calculation anyway with the formula that's shown on the right there. And we can finish that in the next slide. Now we're going to reject the null hypothesis if t is not between t sub 0.97 with 1,738 degrees of freedom, and that is so close to 1.96 that that's what we'll use. Basically, that's large enough to make this sampling distribution to be essentially a normal distribution. Now, to finish the calculation started on the previous slide, we'll calculate s sub p squared, and that's 79.86. Take the square root of that, and we have S sub p, which is 8.94. Now, you may be tempted to want to try to calculate the weighted average of the standard deviations from these samples, but because you go back and forth between squares and square roots, you really can't do that. So you have to do this properly, that is, to go back and calculate the sample variances and then pool or average those two sample variances with the weighting algorithm we've been discussing. So we do our test statistic in the next item here, item 6, and look at t, and it's 3.3 minus 2.4, that's 0.90, and the standard error of that difference is 8.94 times 0.059. Do all that calculation, we get 1.71. So with that information, we got the result of our t-test. It's 1.71. In item 5 above, we said we would reject the null hypothesis if we calculated a value of t that was not between plus and minus 1.96. So here we have a number that is between minus 1.96 and plus 1.96. So we will accept the null hypothesis that the two populations have the same mean. Now, have we proven that they have the same mean? No, of course not. We just simply don't have enough evidence to reject that they could be. Their p-value, thus, is greater than 0.05, and in fact, it's somewhere between 0.05 and 0.10. Now, to interpret this particular situation, as is always the case, you need some careful thinking about the assumptions. In this particular case, there is the concern that the two populations might not have the same variance. And it's important to remember and to understand, I guess I should say, and also to remember that any of these hypothesis tests that we work with end up using some approximations. And so the question is how far off the mark is this particular approximation of using this particular t-distribution going to be under these circumstances? Well, it'll be off a little bit, but we didn't reject the null hypothesis anyway, so we're not likely to have come to the wrong conclusion. However, if we wanted to be more careful about that, we could look at the at this process when we do it properly. All right, I have another example I'd like to work with, and obviously I'm picking examples out of tables that are in the literature. And one of the reasons that I'm doing this is to try to give you the comfort that you can do this yourself, and that you can test your own hypotheses from information that's in the literature. Now, the previous example had fairly sizable sample size. There were two large samples, and it was easy to think about those samples being comfortably random samples. We had a little bit of unease about whether or not the two populations might have had the same variance, but again, we have a way to deal with that. In this example, we see information we've seen before of the Social Security systems versus the National Health Services systems in Europe, looking at health care expenditures per capita in US dollars. So we looked at the first column here, the Social Security systems before. Now I'd like to expand the question to the point where we can compare the two kinds of systems with respect to health care expenditures. So here we have the mean for the Social Security systems for this sample of size 7 is 1,427.6. The mean for the National Health Services system with the sample of size 10 is 1,057. And you notice that the p-value they list there says less than 0.01. So what I want to do with this exercise is to let you check and see whether you agree with that p-value or not. So all we need to do is to do our two-sample t-test using this information. We have estimates, and notice here that they're labeling this column for SD. So what they are telling us is that they're giving us the sample mean plus the sample standard deviation. And for the Social Security systems, the sample standard deviation is $142.5, and for the National Health Services system, it's $334.1. So now if we just go through the 7 steps that we've been through many times now, with this information, we can test this null hypothesis, and in this case, that hypothesis is that the mean for the Social Security systems per capita health care costs is equal to the mean for the National Health Services systems, versus the alternative that's not equal. We're going to use alpha equal to 0.01. We're going to assume that we have independent normal samples from normal distributions, and that the variances for these two populations are equal. The test statistic that we're going to use is the one we've seen on many occasions. Notation is a little more cumbersome, but that's the situation very clearly. We're going to reject the null hypothesis if the value we calculate here is not between plus and minus 2.1315. That 2.1315 should be the value from the t-tables for t sub 0.975 with n1 minus 1 plus n2 minus 1 degrees of freedom, and that's 7. n1 minus 1 is 7 minus 1 or 6, and n2 minus 1 is 10 minus 1 or 9. So 6 and 9 is 15, so it should be 15 degrees of freedom. Now, we do the calculations. We have to calculate s sub p squared. We have s sub 1 squared, or s sub n s, so we have to square that to get the numbers we need, but otherwise we just follow the bouncing ball here, and we get the value for the pool variance as is shown in the second line of the equations of $75,096 squared, and take the square root of that and we get $274 for s sub p. Finish the calculations as shown in the next line, and we end up with a value of 2.75. So what we said then was that we would reject the null hypothesis of the value if the value we calculated for t was not between plus or minus 2.1 or so, and the value we calculated was not between those two cut points, and so we're going to reject the null hypothesis. Now we can look at the p-value for this outcome, and if you look at the p-value for this outcome in the tables, I think you'll see that it's between 0.01 and 0.02. So according to this test of this null hypothesis, saying that the p-value is less than 0.01 is not quite right, because it's a little bit bigger than 0.01, but it's not far from that. So the column in the table that says the p-value is less than 0.01 was either based on a different test than this one, or they made a small mistake. Now I'd like to look at another example and try to give you the comfort that you know beginning to know some things that you might not realize that you know. Here I have an example of independent random samples from two populations of serum uric acid values, sample 1 and sample 2, and there are 10 observations in each sample. And you notice if we add these observations up, we get 10.6 for one sample, which leads to a mean of 1.06, and 16.1 for the second sample, which leads to a mean of 1.61. So we have two sample means here. Clearly the two sample means are not the same. The question is whether these two sample means are sufficiently different from each other to lead us to want to conclude that they came from populations that also had means that were different from each other. So we can set up a worksheet as I've done here, and this time we're working from the individual raw data. So we have to calculate the variances and the means, etc. And I've done this in a spreadsheet, and I would actually encourage you to create this spreadsheet on your own, and just to make sure that you can do it. But if you do that, you end up with the x's and the x squareds for sample 1 and sample 2, and you end up with the sum of 10.6 and the mean of 1.06 for sample 1. You can calculate the sum squared divided by n, which is 10.6 divided by 10, which is 10.6 squared, divided by 10, which is 11.36 for sample 1, and you can go through a similar exercise for sample 2. And you can also calculate the sums of squares, which is 0.824 from sample 1 and 1.669 from sample 2. You can calculate the variance and the standard deviation. So you should make sure you can calculate all these things. And furthermore, you should make sure you understand what they mean, and what they are and what they mean. Now, one of the things we know we're going to have is this estimate of the pool variance. And we have from the previous page s sub 1 squared is equal to 0.09 and s sub 2 squared equal to 0.19. So we can plug that all into this formula and finish the calculations. Now I would also, don't have it explicitly written out here, but you can shortcut this process a little bit by simply recognizing that the numerator of this expression is the sums of squares for x1 plus the sums of squares for x2. And since you already have those calculated, you don't have to calculate the variance and then and then divide to get back to the sums of squares. So you can just use the sums of squares directly. But in any case, you can go through that either way you like and end up with the estimate of the pool variance being 0.14 and the square root of that being the standard deviation being 0.37. So now we have everything we need and we can finish the calculations. The null hypothesis is that the mean for the two populations are equal versus the alternative that they're not equal. And the alpha level is 0.05. The assumptions we're working with are the ones we've been working with, that we have independent random samples from normal distributions and that the two populations have the same variance. The test statistic is as shown at the bottom of the slide here, and by now it ought to be a familiar entity to you. We're going to reject the null hypothesis if the value we calculate for t is not between plus and minus t sub 0.975 with 18 degrees of freedom. Here, remembering that we get 9 degrees of freedom from the first sample and 9 more from the other sample, so together they make up 18. So that leads to the cut point here of 2.1009. So for item 6, we go through the bouncing ball again to get all the calculations done, and we get a value of minus 3.30, and that's clearly not between plus or minus 2.1009 and plus 2.1009. So we're going to reject the null hypothesis. So what's our conclusion? Well, our conclusion is that we have pretty strong evidence that these two samples came from two populations that did not have or do not have the same mean. So we're going to reject the null hypothesis. And we can also look up p-value for that test. Now, I wanted to take you through that example one more time, to take you through the process one more time, but I wanted to also use it to give you some understanding that there's another tool out there that you already know how to use. Now, suppose that the situation that we had here was that these were not one group of 10 people from one population and another group of 10 people from another population, but rather this was one group of 10 people, and the first set of values, the serum uric acid values, were those that were measured before taking eating a special meal, and then the other population were values that were measured from blood drawn after the special meal. So we have 10 people, and we have a measurement before a meal and after a meal for each person. So how can we deal with this? Do we have two independent random samples? Well, that's a little bit of a stretch because the two numbers you have come from one person. So each person is contributing a before and after number. So those are clearly not independent because the level for the person may be affecting that difference, and so they're clearly not independent. So what are you going to do with this? So we have 10 people with before and after measures for each one. But what are we really interested in here in this case? Well, we're interested in the difference between before and after. So we can measure that directly. So the easiest way to do this is to convert it into a problem that we already know how to deal with. That is, we convert it into looking at differences. So here I've listed out, we have person 1 on this spreadsheet. We have person 1, we have the before value and the after value, and we have the difference between those two for person 1 and person 2, etc. And we have the sum of the differences, and we have the mean difference. So here we have the mean difference between the before and after, in measuring this as after minus before, we have a mean difference of 0.55 units. So the question we're trying to address now, well, is that difference, that mean difference of before and after, sufficiently far away enough from zero for us to claim that the true value of the difference between before and after is zero. And if we reject that null hypothesis, obviously we have evidence that the meal had some impact on the serum uric acid value. So that's what we're really after, to see if there's evidence that the meal had impact on the serum uric acid values. Well, we have this difference. What can we do with it? Well, it's really quite simple, and it's very easy to work with. All we need to do is to consider these differences as a sample from a population of differences, and so we have a one-sample problem. That is, we can look, if we work with the differences, we can have a one-sample t-test. So all we have to do then is do a one-sample t-test on those differences. And so what the rest of the calculations at the bottom of this sheet are created with that in mind. And so we can test the null hypothesis. Here I'll use the delta because it's really delta and d that I want to focus on, where delta is the difference between the mean for the after measurements minus the mean for the before measurements. And so we're going to look at delta equals 0 versus delta not equal to 0. We're going to have an alpha level of 0.05 as we worked with. Our assumptions are that we have a random sample of the differences. Not a random sample of the before, and not a random sample of after, but a random sample of the differences. And then we're going to use the t statistic, which is d bar over s sub d divided by the square root of n. And that's all just working with the differences. And this is a one sample t-test. So if we finish our calculations, the rejection region is we're going to reject the null hypothesis that delta is equal to 0 if t is not between plus or minus t sub 0.075 with 9 degrees of freedom, which is 2.26. Now, why 9 degrees of freedom? We have 20 numbers here, 10 before and 10 after. Well, that's true, but we only have 10 differences, and we're using the differences as our unit of analysis, so to speak. So we have 9 degrees of freedom. We do the calculations, and we get a value for the t statistic that's 3.29, as shown here. That's clearly not between plus and minus 2.26. So we reject the null hypothesis that delta is equal to 0 and would conclude by that we have evidence that the meal did impact on the serum uric acid values. And in the same way we've done before, we could look up a p-value for this particular outcome. Now, this is an interesting strategy for converting a problem that might on the surface not be so easy to, might not appear to be so easy to solve, by just thinking about it slightly differently and focusing on the differences, and therefore we have a one sample test. This test is in fact called the paired t-test, and all the paired t-test is a one sample t-test where you look at differences.